Thanks for the introduction, and thank you, thank the organizers for inviting me to this to speak here. So today, what I want to talk about is this L2-Alexander torsions, but I'm going to try to focus on the context of three manifolds. Torsions, so our basic setting would be that you think about some n, that would be any three manifold, and you want to put some adjectives there to make your life easier. Since you're talking about homology, usually you want to put some condition like irreducible, and let's say compact. 3. You can make it. I think I want it also to be, let's say, orientable. 3 manifold. And you can require its boundary to be empty or tori, just to make sure that its order characteristic is just 0. And then for such a 3 manifold, what you want to consider is any L2-Alexander torsion associated to any admissible triple. And in this morning's talk, I think Stephen Friedel has introduced some general notion, and let's recall some of them. So basically what you want, so the data that you need to define this L2-Alexander torsion are basically so-called, let's say, gamma phi and admissible triple. Triple means there's secretly there is another group G. Well, let's say gamma phi G. G is like the target of gamma, and that just means, well, you later you want to twist the chain complex associated to n with respect to some representation of the fundamental group, as we usually do, but now we just require this gamma to map into a countable group, and then there is another direction you can associate with any first cohomology class. You can make this to map into either Z or R in the most general setting. When you want to talk about continuity, you can try to put it R. And by saying it is admissible, basically means that you want there to exist some factorization of phi through this gamma. So that's our basic setting. When you have such a setting, then the idea is that you can basically twist let's say the chain complex associated to the universal cover of n with a representation which is k gamma phi t, that is basically z pi 1n, and it just goes to R G. What it does is that it is basically you can think of this to be a representation of this ring, and it just sends any group element to something that should be represented in terms of things in G and some coefficients. And this guy here, of course, that should go to gamma G. and you can actually use phi to twist your coefficients a little bit by adding another coefficient there. For any given positive constant t. Okay, so if you have such a representation, you can do as what you usually did. Just think about the torsion. So let's say tau 2 of that's some torsion associated to n, and the data here are gamma and the phi, and that is something dependent on your parameter t. That would be some. That would basically be either the torsion of the twisted complex, which is here you can use the representation kappa to represent, and you have here. This is a chain complex whose boundary map is basically 1 times 1 tensor with boundary. And this, in order to speak of the torsion, you want all your boundary maps to give you a cyclic chain complex, and also you want your determinant to be well defined there. For example, I think by a theorem of Luke or Luke and Friedel, if Q is some rational number, then you can always make this you can always make sense of this torsion in the weakly cyclic case. So when this chain complex is weakly acyclic of determinate class. Okay. If that assumption holds, then this torsion would be something that lies in that is basically the alternating product of the torsion coming from each dimension, and that will give you a positive number. Otherwise, this is not well defined. I mean, you cannot properly speak of torsion in that case. So by convention, we just put it to be 0. This definition here follows the paper of Dubois, Friedel, and Luc. So this is basically our definition of the so-called L2-Alexander torsion, which is associated to the specific twist here. So you actually think of this this t to be a positive real parameter that so associated to each t you can have a real value, and then this thing here would be some representation, and this is a chosen cohomology class. I guess in this talk we want to vary this class. So these two are data that are fixed. So the upshot is basically that associated with this triple phi gamma g, then what you get is basically a function that goes from the positive numbers to a priori either positive numbers or 0. And probably you should just think of this 0 to mean that the torsion is not so well defined there, so you don't really want to make much operation in that case. It's with respect to multiplication, this non-negative numbers break into 0 and all the other positive ones. The other ones form a group, and the 0 seems to be a safe place to record those exceptional values. Okay, and a couple of remarks about this definition here is that yes. So I think you want to make some assumptions. So I guess in this talk, I will try to convince you that if you make G to be a residually finite group, then the output torsion would be a continuous one. Sorry? Yeah, you can actually show that the actual value all lies in positive numbers, and it just avoids 0. Or if it's 0 somewhere, then it's 0 everywhere. That's what we try to see. And just a couple of remarks regarding this definition here. One thing is that here, in order to define this torsion, you need to choose a CW complex structure of this manifold N, and then it lifts to the universal cover. And if you switch to a different CW complex structure, you may get a different function, and that function may differ from the previous one by a factor of it's of the form just some monomial of T for some R. So you're talking about function, and this is ambiguity factor. So in this talk, we'll think of the L2-Alexander torsion to be something that is defined up to this change of factor. And I think for closed hyperbolic three manifolds, you have so in the original definition, you can actually consider also an Euler structure, which basically tells you which choice of basis you want to take in this CW structure. I'm just, let's see. Yeah, when phi is lies in reals, probably you will get this to go into real. Okay. Yeah. It's, yes. Right. And eventually we will try to show that this function would grow like t to the b to one end and shrink like t to the a on the other end. Yeah, it asymptotically to those monomials, and then you can define the degree to b minus a. That's it's the closure of the image would be the kernel. Right. Any other questions regarding to what we have talked? With if you consider those Euler classes, then you can actually get rid of this ambiguity, and that actually has some nice consequences. For example, then you can try to consider whether or not the function you define is actually continuous in phi. But at this point, well, since we have this ambiguity, we can not directly talk about its continuity about the cohomology class. So this is basically the the definition of the Alexander torsion. And just from some general experiences of algebraic topology, you might have the feeling that, okay, chain complex to torsion is something like a matrix to a determinant. That's so in this sense, we can try to also get matrix version of that torsion that is basically known as the regular Fourier-Cartesian determinant. So basically, instead of considering this chain complex or the boundary operators, can consider matrices, which are basically matrices. For simplicity, I'll just consider square matrices that are that have entries in this group ring. When you have this setting, then you can also define then we can define there is a closely related chain complex to this matrix. You can think of any matrix to be just something like z pi, which pi is just a group, z pi to the plus p, and you take a to z pi to the plus p. Just turn it to be a boundary operator in a chain complex. And then you can basically talk about the torsion associated to this complex. The torsion. And you just take the kappa gamma phi t for this chain complex. And that will basically give you the turns out this is equal to either the usual Fourier-Cartesian determinant valued in G of the twisted matrix A, which have entries inside this group ring. This is in the case if so if the equals 0 and otherwise you can define it to be 0. Okay. where this thing here is basically the Fugler-Carlson determinant. So from this expression, you can basically see that if you choose to, if you do this convention by putting it to 0 when the torsion is not well defined, then in this case, it is basically or it is basically generalizing a notion for matrices, which is something called a regularized version of this Fugler-Carlson determinant. It is the usual one if the matrix is somehow non-degenerate, and it is 0 if you have a non-trivial kernel. So I'll just denote this to be. And this. Huh? Not necessarily. In some cases, you will get like infinity or 0 values. You just make it value 2. Make it value 2. Yeah. Yeah. Let's see. Yeah. I think this turns out to coincide with this weakly acyclic determinate class condition. If you check those, the only exceptional case where you cannot directly tell if it's determinate class. Yeah. And this thing here is denoted to be RA, just to distinguish it from the usual Fugler-Carlson. Other questions? All right. Please.
The same question there. I mean, I thought that implicitly the statement is that if it's weakly acyclic, then the corresponding Laplacian or the operator is determinate.
That's again over rational coefficient.
But rational doesn't make sense because phi is in R.
Right. So if you're talking about, I mean, t varies in real numbers. If you require that condition, then a priori you will get those boundary operators that are represented by matrices over Rg. Yeah. And in that case, weakly acyclic does not imply the existence of the determinant class. Yeah, you also put it 0. Yeah, so it's a little bit, yeah, yeah. So basically 0 means that we don't know what to do, and we just put it there. Exactly. Yeah, and then later we'll try to convince you that in many interesting cases, there's nothing to be thrown away. Everything will lie in the positive range. Okay, just a couple of examples that Stephen mentioned in the morning. One of our basic example is that, oh, by the way, I'm mentioning this matrix version for this torsion basically because later I'll try to focus on the determinants of matrices because they're easier to deal with, and for torsions, they're basically alternating product of those determinants, and I just claim that they can be dealt in the general case. Okay, so the first example, or the one that we're most interested in, would be that your group G is basically the same group as pi1n, and your gamma is the identity map of pi1n itself, and let's say phi can be whatever inside. Depending on your flavor, you can make it over Z or over Q. And for such objects, what is associated is called the full L2-Alexander torsion associated to the class phi, and it's going to be denoted as tau 2 n phi t. And Stephen has listed a couple of nice properties for this function. For example, its value at 1 will basically give you the exponential of volume of n divided by 6 pi that is known. And also, if phi is a fibered class, in the case of three-manifold topology, then your T or your torsion can actually be expressed as monomials outside entropy range, and that give you some basic situations where you can actually tell what the value of the torsion is. And for other places, well, just it might be 0, it might not, and that's the task that we want to do here. We want to make sure those values are well defined and continuous. So in order to get something, or in order to extract any information about the full torsion, what you want to do is that you want to make a sequence of this target group G that are easier to study. And this a typical class of such group G comes from this general construction. Which virtually are billion. So what you do here, if you are studying three-manifold topology and its virtual properties, you might prefer to study those finite covers of a group. And if you look at this setting, you might expect that G is some finite index subgroup of pi1, G is some finite quotient of pi1n, but that's not actually true. What you do is basically that you first take a finite quotient, which looks like pi1 of n goes to some group gamma, and then out of it you can this is a finite quotient, so its kernel would correspond to some finite cover of n. Let's say some normal cover of n, so that the covering transformation group is basically your gamma. Then your actual group G that you want to consider in this case is the is basically the extension of gamma by the abelianization of n. So that's something like this here. And it goes to some group G. This goes to gamma, that's equal to gamma. And in this way, you get a unique extension, which is a canonical object associated to any quotient gamma. And this thing here is a correct G that you want to look at in the setting of L2-Alexander torsions, just analogous to those finite quotients. And in this case, because you are basically taking the abelianization of this entire N, you can actually make you can take whatever phi so that it's automatically admissible. Just because you're basically taking the entire abelianization to be the group G. The condition here is like this. The admissible means that at first I have a gamma to some group G, and I have a class phi that goes to R, and basically the condition means that I want it to factor through. So if you think about the definition here in the essential expression after you applied this homomorphism kappa, then all the data are actually either coming from the group G or coming from those images inside this R. So the pi1 of N is gone, and you can actually work with this factorized homomorphism. Okay, so so in the second type where your G is virtually abelian, then the most trivial one is that where your gamma is just a trivialization, and your group G will basically become the abelianization of your group N. So if what happens here? So you have only take the trivial quotient, and your G will basically become the abelianization of N. And in this case, with respect to any phi, the corresponding torsion is basically the let's impose some further condition. When phi is the integral class, then what happens here is exactly what Stephen described in the morning, associated to. So if you consider the case of Alexander torsion associated to phi, there is this this torsion which is essentially just an Alexander polynomial, and then your torsion function is basically given by the by scanning the by varying the Mahler measure with respect to the parameter t. And just to be specific, let's focus on what happens to a group A. then in this case, what you get is that then you can basically get your Alexander torsion associated to regular determinant of your function kappa phi gamma t of A. This function is basically the function of the form okay. Just like T is scanning all the roots of the associated polynomial, where determinated by the polynomial it is a Laurent polynomial of the form determinant over Z this is a test, so this is yes, if you fix this if you fix a cohomology class, it factors through a rank 1 group. So basically this you can specialize to a single variable that is due to this cohomology class. If you do not specify this phi and you take the determinant, that will give you a determinant that has several complex variables z1 to zb, where b is basically the rank, the Betti number of the first cohomology. But if you specify a cohomology class, then you can. Gamma is which little gamma? Right. It's just an abelian line. It's yes, exactly. Right. Yeah, that's essentially what Stephen talked about in the morning. And just look at this. If you look at this polynomial, and it has an expansion of the form d times maybe z to the something, then times the number of roots. If you have this factorization, then you can actually explicitly write down your determinant function that looks like that you're letting t to go from 0 to infinity, so that you're scanning how many roots are there remaining outside this this circle, and you multiply those things together to make your coefficients, and then the rest, the count of the roots that you have scanned would become the power of t that appears here. Okay, so the important thing here is that we want to inspect what happens to this picture, and we want to see that whether or not we can make a limit process from those virtually abelian quotients to the original group, and I want to make sure that this limit procedure will preserve some of the properties that we observe in the picture. We'll specify what are those. So this is what Stephen described in the morning. The graph of this function would basically look like, at first, it's some constant because it's coming from a function. And in the end of the day, that would become some, essentially just some monomial. Okay, and in between, you might have, okay, first that's a horizontal line, and then you have one, maybe you have come across one root, then that becomes a line. And then it becomes maybe a parabola and then a cubic curve, etc. And the degree basically increases. And you might see a couple of bending points where the where your function is not smooth there. And that sort of give you a feeling that your function of this type give you some values that are in some sense multiplicative, and it is more, at least it is helpful if you turn this picture to the log-log plot. Then what you see is that all the curves would become just piecewise linear ones. At the beginning, it might be just some constant d. So you will see something like this. It goes from the negative infinity to positive infinity. And at the beginning, it would look like some horizontal line. And then at some point, it starts to bend up. And then maybe some other point, it bend up more and later. So it's just basically a piecewise linear graph in the log-log plot. Well, and moreover, yes, in the polynomial case it is. Yeah. And moreover, what you can actually see is that the log-log plot is actually convex. So it's piecewise linear. And if you check it to actually be convex, because if you continue to go along some segment at the bending point, you don't want to go further, but your parameter t becomes a variable that is going to increase, so it will actually bend up, and you can actually see down and write down the formula to see the convexity. Just to describe the original picture, we just translate what we have seen here to say that this is multiplicatively convex. That condition basically means that your function would satisfy the condition t0, t1 is greater or equal to let's say root of T0, T1, some condition like that. Okay, so what's special about this property? Just based on the observation here, what we can set as our goal is to show that for the full version, the tau or its matrix analog is also, let's see, it is also multiplicatively convex. Once you can show this, you will be able to tell that if the graph is 0 somewhere, you can actually derive from the condition here that the graph must be 0 everywhere. That is one of the observations that you can get from this convexity. Another is that if you can actually show the convexity or multiplicative convexity, then the graph itself would necessarily be a continuous one. If you think about the problem itself, then it's actually strategic. In strategy, it's actually easier to show the convexity rather than showing this continuity. Because for continuity, you need to look at a sequence of values and see whether or not it converges to somewhere. And for multiplicative convexity, you only need to look at an expression that is about 3 points. And then what you do is basically make your... so you have already observed this expression for virtually abelian torsions. And then you want to take a limit process to show that this inequality also holds in the full version. That is basically the observation that we want that we get from this virtually abelian case. Okay, so I think I have about 10 minutes left. I can give you some. I can sketch some idea about actually showing the multiplicative convexity of the limits. So in our setting, we'll take or let's say we want G to be any residually finite so that we can actually approach it by finite quotients, and then gamma phi G to be an admissible triple. And then you want a matrix. You're basically keep in mind that this matrix was something like the boundary operator in your chain complex. So you want this matrix to be something that has this form. But for continuity, I think it's okay to make it real too. And then, so the idea is basically that you want to take the virtually abelian case and make it approach the limit case. So basically you want to take pi 1 of n and take a sequence of so this thing here is the identity. Sorry. Just for for convenience, let me try to show this pi 1 of n case. For 3 manifolds, it's known to be residually finite, and this gamma to be the identity, just a full torsion. Then you will have a sequence of finite quotients that such that the kernel, the common intersection of the kernel will converge to your pi n. And from this sequence, you will be able to derive a corresponding sequence. Just by extending using the homology. And then, so associated to every G, you will get a corresponding gamma n. Phi is still itself, and a Gn. And then, associated to this guy, you can define so we try to write down all the terms we need, and we try to look at what happens there. Now, this is the twist of A by the quotient group Gn using parameter t. And then you want to look at the function Vn of t that is determinant R of A and t. And by our observation, we have seen that for any finite number n, then this function is always multiplicatively convex, which means which basically means that it satisfies the expression above. So the convexity tells you that for each n, then you will have some expression like this. And at this point, you just want to take the limits on both sides as n goes to infinity, and you want to, if both sides genuinely just converge to the full case where n becomes infinity, then this inequality will be preserved. But life is not that easy. What you can actually get is basically the left-hand side would become, you will usually get a semi-continuity, so what you can get for the left-hand side is an expression of this form, and in order to continue this inequality, you need to take limited sup of the right-hand side. But the right-hand side looks like this, where it is a determinant of some matrix A, but the value T is basically assigned to the T0, T1 square root. And you cannot, in general, just continue this expression to get it equal to the right-hand side to prove the inequality. So we do want the right-hand side to get the limit of sorry, which one?
So why is the point
Oh,
better than just one of the endpoints, where you get only the inequality, and for this point you get the equality? What is different?
I think the multiplicative convexity is something like this, right? Yeah.
I mean, if you expect an equality there, so why would you expect an equality with the first?
The first is something you can derive based on the property of Cartesian-Fugletti determinants. So it's just a fact that this is not it's not in general equal, but greater equal. Right. I mean, these two steps are both okay, and we can always get them to be true. And essentially, you want to prove that this inequality implies the inequality with n replaced by infinity. So you want to continue to get to. So you want to continue to get to something like this. But I'm saying that in general, this is something that you cannot you cannot prove. I mean, it's in general not true to get it from here to here. And one of the conditions that you can make this inequality true is that if A is a positive matrix, and actually it's easier to show if A is actually a matrix greater or equal to some uniform constant. Okay, so at least if we try to realize this strategy, you will say that, okay, if my matrix A here is actually a positive matrix with no small eigenvalue, no accumulating eigenvalue near 0, then I would be able to pass from the virtual abelian quotients to the limit to prove the multiplicative convexity. And in general, this is, I think I'm out of time. So in general, this is not true. So you really need to do some trick to make it happen. And I claim that the trick you need to do is that you look at another matrix coming from A, but it looks like A star A plus epsilon I. And you just adjust V and T accordingly. at the end of the day, you don't. Besides this limit process as n goes to infinity, you also want your epsilon to go to 0, and there are two limit process involved, which also preserve certain semi-continuity, like this here. And you also need to rearrange your matrix because of some anti-commutativity contained in this expression. But I just claim that if you make suitable modification of this idea, then you can actually prove the general case based on this naive idea. And then that will tell you the multiply convexity, which implies the positiveness and the continuity. Mm-hmm. Yes. Right. That's true. That's what I was saying. That if this operator commutes with a star, then that would tell you the positivity of this matrix. It doesn't. So what you do is that you consider kappa. So I'm just writing down the expression that you need to check of T1 divided by T0 of a positive operator, which is a n star. Then plus epsilon I. And use this operator, you can actually check the continuity. This is a positive one, so if you apply... you're not applying kappa to... I mean, you can... To make this argument work, you can make this to be just any ANT to be positive and greater or equal to this I epsilon. Right, you're just taking the determinant of this matrix, so you want the positivity for this matrix. So I guess I'm already out of time, so I'll just stop here and welcome for any questions.